this poloclub.github.io transformer explainer. So here you can see, first of all, we have some slides that explain the architecture of the transformer. We can close them now, but let's focus on the interface. First, we have an input that will generate. You can see here, data visualization empowers users to visualize. Here you can write whatever sentence you need or whatever sentence you would like, and then you can click generate and it will generate. So let's click generate. You can see now it do one forward pass and then it tries to generate, and now the model generated that. Let's click another time. You can see it will generate another time to visualize the world. So data visualization empowers users to visualize the world, and then click generate around them. First, here you can see we have some embeddings. So we first start by inputting some sentence, inputting a sequence. As we said in here, we first start by inputs. These inputs will be processed by 2 steps. If we click on the embedding here, you can see we have 2 steps. We have token embeddings, which are here. We have these IDs. You can see 6,601. So these words, these tokens are mapped into integer IDs. Then these integer IDs are poor representations. They don't convey the semantic meaning. We need another way to represent them. So the best way to represent the words is via the token embeddings and turn them into embeddings, into vector, dense vector embeddings. After that, we preserve the position encoding. Here you can see we have this input embedding layer, which will turn the token IDs, integers, into vectors, high, rich representation vectors. Then we preserve the contextual meaning via this layer, positional encoding layer. Here, this position encoding layer will preserve the meaning. You can see data is at the first position, visualization is at the second position, 1, M is 2, powers 3, uses is 4, 2 is 5, and so forth. So we have token embedding, and then you can see here tokenization splits input text into tokens. Tokenization segments input text into tokens, small units like words or subwords or parts of the words. GPT-2 Small has 50,257 token vocabulary, each with a unique ID. In the token embedding step, every token is matched to a 768 number vector. So each token is converted into a vector of size 768 number inside the vector from a large lookup table. And these vectors are land. These are land vector representations. The model will, when we train the model later, the model will adjust and fine-tune these values inside each vector to best represent the words. And then similar words will be clustered together. The similar words will be clustered far away. These vectors are learned during training to best represent each token's meaning. After this, we have this position encoding layer, which we can see here. Word order matters in language. So the word order or the order of the words matters. Position encoding gives each token information about its place in the sequence. So since transformer as a standalone architecture doesn't learn the order, doesn't capture the contextual meaning, we need to preserve them. GPT-2 does this by adding a learned positional embedding to the tokens embedding. But newer models may use other methods like rope, which encodes position by rotating certain vectors. All aim to help the model understand order in text. After this, after we have processed the text, we can input this processed text into the encoder, which contains the multi-head attention layer. Here we have the you can see we have now the transform block, which is this area that is bordered. If you close this, we have the transformer block. The transformer block, which is the bordered area. We have multi-head self-attention alongside with the multi-layer perceptron. And if you go down here, we have after the embedding. So here we have embedding and we have tokenization. We have token embedding. Here we have the transformer block. The transformer block consists of 2 things. We have the multi-head self-attention, and then we have after this, we have the multi-layer perceptron. Here, multi-layer perceptron MLP. So these are the 2 main components. As you can see in the image, we have multi-head self-attention alongside with the feed-forward network. The first thing here, let's start by the first thing, multi-head self-attention. Multi-head means we apply several numerous attention processes in parallel. So here, if you click on them, self-attention lets the model decide which parts of the input are most relevant, are most significant to each token. This helps it capture meaning and relationships, even between far apart words. In multi-head form, the model runs several attention processes in parallel. So in multi-head form, the model runs several attention processes in parallel, each focusing on different patterns in the text. And here you can see inside the multi-head self-attention, we have three key matrices, three important matrices. We have the key matrix, query matrix, and value. The key here, if you click on this, we have query, key, and value. So the key and Q and value are three learned vectors that the attention will learn and update them. To perform self-attention, each token's embedding is transformed into three new embeddings. So each token's embedding, the data, visualization, each word will be converted or transformed into three new embeddings: query, key, and value. You can imagine this as an analogy. We have the search engine Google. When you type in the text, that you type into the search bar, this is the query. So here we have this search bar. You can search in here, what is machine learning? This is the query. This is what you are looking for, what you are searching for. What do you want? What you are looking for behind the scenes. This is the query, the Q. When you click enter, Google suggests multiple websites: IBM blog, Wikipedia blog, Datacam blog. These are the case. These are the case that suggest themselves, that say, choose me. I have the answer. I am fit to you. I am appropriate to you. Then we try to multiply, here you can see, we try to multiply the K by Q and see how much or how far or how close these two together. Then when we decide that this is the closest K to Q, we choose, or we assign them the highest weight to its corresponding value. The value is the actual content, the actual information inside the K. So K will provide us with this V. This is the V, the actual content that will be used or will be passed. So here we have, you can see these parameters, weight and biases. So this transformation is done by applying different weights and biases to each token embedding. These parameters, weights and biases, are optimized through training. Once created, queries compare with keys to measure relevance, to measure similarity, and the relevance is used to weight the values. So if it represents a higher measure, a higher similarity rate, a higher closeness rate, then we assign a high weight to the value. If it's a low relationship or a low correlation between K and V, between Q and K, we assign a low weight to the V. You can see here, them is assigned a high probability, whereas us is assigned a low probability. So you can see here, the V is passed through here, and then we have data moves through the residual connection, then we have them as 98.32% as a high weight. So we say that the Q is multiplied by the K, and then we scale it via, if you click on here, it will multiply the K by the Q, then it scales that via this equation, Q multiplied by the K transpose divided by the square root of the dimensions of K, then we plus the mask. So here we have the dot product, the multiplication. We multiply Q by K transposed, and we transpose the K because in the multiplication of algebra, we need to transpose the other matrix in order to be compatible to multiply the two matrices or the two vectors. Then we mask it to prevent access to future tokens, and then we have the softmax. We apply the softmax on this masked attention. Then we have a probabilities here. You can see we have some high probabilities. For example, the word visualization is assigned a high probability. You can see 84, whereas some words here have low probability. For example, 0.03. Then we have this value. We will take these values and then will be passed as the output here. Then we'll go through the multi-layer perceptron. So the main idea of the attention here is that it's a mechanism in machine learning that directs deep learning models what to focus on, what to prioritize. So which parts here should we prioritize? Should the model prioritize and gives the most attention and pay attention to? After this, we have the multi-layer perceptron. The multi-layer perceptron is a feed-forward network that refines the land representations by the attention. Here we have, you can see MLP. So the attention output goes through an MLP, multi-layer perceptron, to refine token representations. A linear layer, which is a feed-forward layer, a simple feed-forward layer, changes embedding values and size using learned weights and bias. Here in the MLP, also we have learned weights, learned biases. So the embeddings here are learned, the KQV are learned, the MLP weights and biases are learned. So you have here three main areas that those areas are learned. A linear layer changes embedding values and size using learned weights and bias. Then a nonlinear activation decides how much each value passes. Many activation types here in the MLP exist. GPT-2 uses GLU, which lets small values pass partially and large values pass fully, helping capture both subtle and strong, robust patterns. After this multi-layer perceptron, here you can see we have this residual connection. And also here we have a residual connection. You can see we have this residual. We pass the raw input as it is without any transformation as the output of this attention or multi-heads of attention. So we combine the transformed data that goes through this attention layer. We combine it with the raw unchanged input from here. We pass it as a residual. You can see residual connection. What is the main idea of residual? Residual connections helps to stabilize the training and the gradient flow of the neural network. So transformers have extra features that enhance the model performance, but aren't core to understanding the basics. For example, a residual connection adds a layer's input to its outputs, keeping information and learning signals from fading, keeping them to not fade, to not vanish through many layers. In GPT-2, it's used twice per block to train deeper stacks effectively. And the same idea, we apply another residual connection in the multi-layer perceptron. So we take the inputs of the multi-layer perceptron and then we pass them here to combine them, to add them with the outputs of the multi-layer perceptron. So here you can see we have residual connection. And also here you can see the layer normalization. So if we return to the image, here we have the inputs to the multi-head attention. We add a residual connection and combine the untransformed version with the transformed version, and then we have the normalization layer. The main idea behind the layer normalization helps stabilize both training and inference by adjusting input numbers so their mean and variance stay consistent. This makes the model less sensitive to its starting weights. This makes the model less sensitive to its initialized weights and helps it learn more effectively. In GPT-2, it's applied before self-attention, before the multi-layer perceptron, and once more before the final output. Then here you can see we have 11 more identical transform blocks. So we have the same block as this, but multiplied by the nx11. So we can slide between them. You can see we have another block, a third block, and each block tries to learn different representations, different patterns, different weights, and trying to capture the semantic and syntactic representations of each sentence. So here, this block here, you can see, is multiplied nx times. nx times. They multiplied this block, you can see here, the transformer block, they multiplied this 12 times. So we have 12 of these blocks that will learn the representations in parallel, fully parallelizable manner. After this, so we have here 11 more identical transformer blocks, and then we have the probabilities. You can see here we have the probabilities, and then probability of them, the word them here, token being sampled. We have some sampling techniques here to choose the best next word. You can see we have the scaled logit. So here, temperature hyperparameter. Temperature is the most important hyperparameter in the transformer architecture. It works by scaling the logits before turning them into probabilities. A low temperature, for example 0.2, makes large logits even larger and smaller ones even smaller, favoring the highest scoring tokens and leading to more predictable choices. A high temperature, for example 1 or above, flattens the differences, making less likely tokens more competitive, and leading to more creative outputs. So if we decrease the temperature, you can see the model is the most deterministic approach. So it takes a strong deterministic approach. So here you can see the word them takes 100%. Whereas if we increase the temperature, the model becomes creative and creative and creative. So the more temperature, the more creative the model. The more creative the model. You can see here the probabilities get distributed over the tokens. And here you can see again we have the top K filtering. We choose the K equals 5. Then you can see the sampling strategy. Finally, we need a strategy, an approach to pick the next token. Many exist, but here are common ones. Greedy search picks. You can see here we have the greedy search. You can change the K. So we can choose the first K, just only the first K. We can choose just 2 Ks or 3 Ks. You have K equals 3. We choose the 3 highest performing Ks. And if we increase them, it increases. So here the top K keeps only the K most likely tokens. And top P keeps the smallest set whose total probability is at least P, trimming unlikely ones early. Then softmax turns the remaining logits into probabilities, and one token is picked at random from the allowed set. So here we can choose whether it was top K or top P. If we choose top P, then it is there. Then it generates the word there. Whereas if we choose the top K, then the top K here is the word, you can see the top K, K equals 1, it chooses the word them. So you can play around with that in your own free time. And then we can slide between the transformer blocks. We can go to the third block, fourth block, and see the attention weights here change. You can see here, the attention weights here are different from here. Every block learns different patterns, learns different representations. Until we have here some examples. For example, IEE, this conference highlights then it tries to generate, highlights the importance, generate of, generate. So it moves through all these steps, multi-perceptron, residual probabilities of then it generates. Also you can write your own text. For example, I like reading, generate. Then it tries to generate here. You can see the Q, K, V vectors. I like reading about, generate. You can see here, I like reading about the, generate another time. Now we have the V here combined. I like reading about the history, which is a really nice topic. Then if you go down here, you can read more. What is a transformer? Transformer is a neural network architecture that has fundamentally changed the approach to artificial intelligence. Transformer was first introduced in the seminal paper Attention is All You Need in 2017. So you can feel free to read this paper. Attention is All You Need paper. And then we have and has since then become the go-to architecture for deep learning models, powering text generative models like OpenAI's GPT, Meta's Llama, and Google's Gemini. Beyond text, Transformer is also applied in audio generation, image recognition, computer vision, protein structure prediction, AlphaFold, and even game playing, demonstrating its versatility across numerous domains. And here we can see we have the Transformer architecture. We have embedding layer. The input text is divided into smaller units called tokens, which can be words or subwords. After this, we have the Transformer block. The block consists of 2 important mechanisms, the attention mechanism and multi-perceptron. So inside each Transformer block, we have 2 important core things, attention mechanism and multi-perceptron, and hence the name Attention is All You Need. We remove recurrence, we remove convolution, we just attend to the most important significant parts and pass them to a multi-perceptron that refines the gradients. Then we have outer probabilities, the final linear layer, and softmax says transform the processed embeddings into probabilities. And you can read the rest in your own time. So you are more than welcome to explore the rest of these. And here you can see we have the main idea behind residual connection. Residual connections were first introduced in the ResNet model in 2015. This architectural innovation revolutionized deep learning by enabling the training of very deep neural networks, essentially Residual connections are shortcuts that bypass one or more layers, adding the input of a layer to its output. This helps mitigate the vanishing gradient problem, making it easier to train deep networks with multiple transformer blocks stacked on top of each other. In GPT-2, residual connections are used twice within each transformer block, once before the MLP and once after, ensuring that gradients flow more easily and alien layers receive sufficient updates during backpropagation.